Assalamu alaikum. Thank you, Dr. Ilyas. It's a great pleasure to be here for the second, I think, or the third time in Dubai. For those who don't know us, we are not in UAE. We are headquartered in Bahrain, but we are working also in UAE and Dubai and Abu Dhabi projects. About our company, we are a startup established in 2023, relatively new, but alhamdulillah, we have done some achievements. We are a training partner with Bentley for Blacksys 2D, Blacksys 3D, and drum concept for boss tensioning designs. We got awarded with several awards for our sustainable solutions in foundation engineering, the Bentley Envision Award from the Institute of Sustainable Infrastructure, as well as the Global Distinguished Innovator for Private Sector from the GDI, Global Institute, from Gini, sorry, Global Innovation Institute, regional winner of the 5th Microbial World Cup in Spain by the ISM, International Society of Microbials, and finalist at Sustainable Construction Project here in Dubai, Big Five last year. I'm bringing this because it's very relevant to the case study we will discuss today. We got these awards because we combined the remote sensing INSAR monitoring, calibrating the numerical model, and reducing the quantity of the microbials and underpinning project in Jazan, Saudi Arabia by 75%. But in today's case study, we eliminated the microbials, so 100% saving. This is us featured in the news. The case study is 2 towers in Jeddah, Saudi Arabia. It was constructed, but on raft foundation, and eventually after the years, they saw some deformation, cracks, and they recall the engineers and contractors to bid for a repair and strengthening for the superstructure as well as for the infrastructure and the foundation. The straightforward proposed solution was to underpin the raft with micropiles. So there was a lot of repair and strengthening scope in that project, which involves the superstructure, the columns, the slabs, but as well as the foundation. And here we came in and tried to solve the problem, as we will see. But for those who don't know me, let me introduce myself. I am the CEO and Technical Director of GeoSTruxer. I am proudly a PhD candidate under the supervision of Professor Dipankar Chaudhary at IIT Bombay in the same topic, remote sensing and geotechnical engineering and microbial draft foundation. I'm also the Vice Chair of the Civil Engineering and Environmental chapter at Bahrain Society of Engineers and adjunct faculty at the American University of Bahrain. Sorry, Korean. Sorry, Dr. Ilyas. I know this is Deep Foundation Conference, but as some of my colleagues, I think Ria also showed raft foundation instead of piles. I have met Professor Alessandro Mandolini in Goa 2024, and he's one of the public figure and renowned researcher in deep foundations. I'm not quoting literally what he said, but he told me that he invested his career, academic career, to know and understand the piles deep enough to advise engineers to avoid them. And he says, the best deep foundations are those you can avoid. So this is what we are trying to do here. Again, and unfortunately, as we are talking about over-conservatism in the soil recommendations and the soil reports and our designs, we tend to presume that the soils are weak. And we are, as many of you, keep getting surprised by the assumptions of the bearing capacity. There is no as such as called bearing capacity of the soil. Bearing capacity is a system property, not a soil property. So you cannot measure the bearing capacity of the soil, but it is related to the system. It is related to the foundation size, geometry, the loads, the superstructure, and the ground profile. But we tend to assume that any project consists of sand or loose, medium to dense sand or granular soil, reclaimed island. We tend to assume by default it will require deep foundations or ground improvement. We have been lucky to eliminate deep foundations and piles in many projects, sometimes reducing them from 300 and 500 piles to 0. So the lessons or the takeaway, even before we start the case study, is let's not assume the soil is weak. The soil might be loose, medium dense, but the load might be also a little bit, and the soil can bear it. These are the two towers located approximately near to each other, and both of them are constructed about 45-meter height, constructed 10 years ago. And they notice there are cracks and uplift impacting the foundations and the basement, which is a raft foundation. And of course, they didn't install any monitoring devices or instrumentation. And here comes the role of remote sensing, the INSAR. For those who are not familiar with INSAR, it's a technology. We are using it depending on a satellite data. And it is the only technology that allows you to travel back in time till 2016, which Sentinel-1 satellite from European Space Agency was available. So from 2016 till today, we can get any deformation of any infrastructure or superstructure or ground or highways or dams till today with an accuracy of plus minus 4 millimeter. So we did consult INSAR to see the trend of the deformation of this building and this tower from 2016 till today. And we will explain how the INSAR as a satellite technology works. From INSAR, you don't get only the deformation. You get the surface moisture content. So up to approximately 5 centimeters from the ground, you can see the accumulation of the groundwater. You can understand the seasonal change of the drainage condition and the moisture condition of the soils. So we noticed that there is a seasonal impact of the water conditions on the two towers. The crack was up to 3 millimeter, and for those structural engineers, I think you limit the cracks to 0.1 or 0.2 millimeter. We have cracks reaching up to 3 millimeters in the basement walls. This is how INSAR work. You don't need to install any device on the site. You don't need to take any permission from anyone. You just need the dates and the coordinates of any building or any infrastructure. The satellite, whether you ask it or not, it will keep restoring the data and saving the data for any infrastructure in the world, almost covering the whole globe. And it will, each time it will pass a constant object on the ground, it will take the radar data or the radar waves. It's not optical satellite. You don't see images. You see radar waves. And the difference between each image and the next acquisition is the phase difference that we can convert it into millimetric deformation. So we use Sentinel-1, and Sentinel-1 data is available for free for everyone, but again, it needs post-processing to convert it into deformation. We developed our own algorithms and platform to convert these data not only to deformation, but also to sensible engineering measures that we are more familiar with as structural and geotechnical engineers, such as the tilt or angular distortion. So you can see, especially in the lower building, we have more differential tilt or settlement. And this is because this structure is more light or lighter than the next structure or the upper structure, and it is impacted by the seasonal fluctuations of the groundwater level. And you can see the deformation reaching up to 40 millimeter upward with an oscillation of plus minus 9 millimeter per year. This is the angular distortion. I believe that was the tilt. So we can see clearly the differential behavior of the lower building, especially. And we can see the time series data of the deformation, and we can link it with the weather data and with the rainfall data and with the flood on the sites and with the specific events that could take place. If you notice in May 24, there is an acceleration of the deformation on the chart on the left. And when we investigated, we noticed that there was a micro-tunneling happening at the same period next to the building. So we could associate the deformation acceleration to that micro-tunneling activities. So in another word, INSAR is a useful forensic tool to be used for geotechnical engineers or structural engineers who want to do root cause analysis of what went wrong. And we can see also the trend, the accumulative deformation along with the time. And we can predict, of course, the deformation in future. So we have a moisture content oscillations, groundwater table fluctuations as well. We have seasonal changes in the winter and the summer. And we have a hydrostatic pressure acting upward on the raft foundation, lifting up my whole building and lowering down. And with these cycles and oscillations, we have a problematic deformation and impact. So there is a differential movement, and the basement was damaged, but this is one of the main issues in the superstructure that our client is trying to solve, which is their scope. Our scope is limited only in the foundation design. So we did a 3D fully coupled analysis. There was sand, fat clay, and the coral limestone. We suspected that the fat clay might induce some swelling or consolidating behavior, but we were not sure, and there was no enough testing in the soil reports. But from INSAR alone, we could understand that there is no consolidation. More or less, the deformation we noticed was seasonal. It was linked with the groundwater regime, not with the consolidation, so we eliminated that. And also, we did run one case in the numerical model with the consolidation, and it was not governing or controlling. What we have proposed, instead of underpinning the whole 2 towers raft with micropiles, we suggested to add another layer of raft foundation, but the only constraints was the architectural height of the basement. They want to keep using the basement. And here we suggested the post-tensioning raft foundation. So we added another layer of post-tension raft foundation. And for those who don't know the post-tensioning, the advantages of the post-tensioning is to reduce the thickness of the concrete and to reduce the steel reinforcement quantity, taking the advantage of the pre-compression applied on the raft. You can, it's not fixed rule, but a rule of thumb, 1.5 or 2 meter RC raft foundation can be reduced to 800 thickness post-tension raft foundation. We checked, of course, many scenarios in the numerical models, and also the serviceability limit state, ultimate limit state, using the Eurocode design approach. We compared it also with the structural team. We have a fully coupled analysis between the ETABS, SAFE, and geotechnical. We do have a final compression deformation of 18 millimeter approximately, and the maximum load case gave us 40 millimeter downward. So we don't have the uplift issue anymore. We produced the design and the spring values to be used for the structural engineers after the coupling is completed. And one of the main points, I would say, for geotechnical engineers, we know that, but for structural engineers, there is no raft foundation can be used without finite element, 3D finite element, 3D finite element, whatever the software you are using, and there is no raft foundation can be used with a single value of Ks or the modulus of subgrade reaction. So this is another takeaway I want to highlight. In our previous project, where we took the sustainability award, we have been able not to reduce only the cost, but also the embedded carbon footprint by 80% approximately. And in this project, I would say we have reduced 100% of the embedded carbon compared to the underpinning of the micropiles. Key takeaways, please do not assume that any repair project requires underpinning or strengthening for the foundation. Try to always investigate the root cause analysis, what went wrong and how to solve it. Integration between geotechnical and structural engineering, leveraging the tools available like remote sensing and the INSAR. The data is available for free, so you can use it. Why not? And that's it. I think I am 1 minute earlier even. Thank you. Yeah. Sure. Thank you.